them. There you go. Just say hi to them.
Okay, so with our weak acids here.
I don't want to be big.
YouTube channel has like 20 videos
Okay,
on every video.
so this is just what we talked about before, that weak acids only partially ionize. In other words, only a small percentage of the molecules of weak acids are ionized in solution. Majority of them are together. So just like you have in your beakers on your table, right? You have a lot of HAs, or you have some HAs together, some HAs apart. To be honest, one thing, I like these models because once again, it kind of gets us at a magic school bus idea. But in order to truly represent a weak acid, I would have to given you 100 of these pieces, because most weak acids only ionize 5% or less. Meaning, if you had 100 of these, only 5 of them or less would be broken apart. So keep that in mind with our models, because we only have 10, that it does exaggerate it a little bit more in how we're looking at it. Okay, here's a picture. This is the same thing we've just made on your desk, but just in your notes, to remind you the difference between the strong and the weak. Okay, now another reminder before we start calculating pH is remember how we talked about that H+, if it's in water, which it always is. So that's another thing our beakers are not showing, is they're not showing water, but there's water everywhere in that beaker. It just gets too busy for the eyes if we also add water to the picture. But there's water in there, and anytime there's water, every single one of these H pluses is going to do what? Bond with the water. So it never really is H plus, it's always this, but we use them interchangeably as chemists, right? So the H plus, this is like the shortcut version. Oh, I must still erase it.
Trying to erase it?
Right? So this one is the one we use, but this is really what it is. So just kind of recognize it's one and the same.
Whose idea was it to do that?
Yeah,
Like, it doesn't make any sense.
So pointless.
That they should have just kept it as H3O+. I don't
This
know.
just makes it more
I'm
confusing.
guessing some lazy chemist who wanted to write H+ instead of just H3O+.
He's like, this will save me 0.2 seconds every single time I write it.
Well, you know, chemists are also the ones
By
who
the time he
abbreviate
died, he saved himself.
Dang it,
the
this
word
is something
mole
else.
to MOL. So, you know,
That extra letter is
something
too
much.
much.
Now,
They ended up saving themselves
weak
like
acids,
5 minutes at a time throughout their
I
life.
still have them up here, but we mentioned like having the strongs memorized and of them will be helpful as we go. There actually are some hints that will, in problems, that also tell you if it's strong or weak if you forget which ones they are. Key thing here is that equilibrium arrow. Weak acids exist as an equilibrium because some are together and some are apart, right? Where if it was a strong acid, you would only have a full forward arrow, okay? Now, this is the same two equations, just this is the true, accurate way of showing this with water. This is we've taken out the water, okay? Since it's an equilibrium system, we can write an equilibrium expression known as capital K. So what's the setup for any K? Product over reactant, and what do we not include?
Solids and liquids.
Pure solids, pure liquids, which in this case I have a major typo on mine. Is it on yours?
H2O.
Yeah. H2 is not aqueous, it is a liquid.
What?
I know.
I didn't know that was.
So that means it's not included, so our expression would be H3O plus A minus, and I'm going to explain what A minus here is in a second,
Oh yeah.
over HA. Now, we use they call it Ka just because it's for an acid, but keep in mind it's the same as any other K. It's just products over reactants. Okay, for a smiley face, fill in that other Ka for me if we were looking at that equation. Give me a pencil drop when you're done. You want a friendly face?
I don't know, you gotta have the good to feel the bad. Yeah, you have to have the bad to feel the good.
I think our test in this class gives you that side.
Whenever I look at multiple
There's a good pencil drop.
I dropped it on the back. That was loud.
That was impressive.
Did I shake a beaker? Does this actually happen?
matches mine, give yourself a smiley face. Okay, now let's clarify A minus before we go on. A is not an element on the periodic table, by the way, in case you thought it was. HA is like a generic way to talk about any acids. Because all acids have an H, right, because they give it up. And then there's the other half of it. So here's a few examples if you want to just write these off to the side just so like as you keep going you don't get confused of it. So like if this was HCl, then A is Cl minus.
Could you just,
Go ahead.
does A just stand for acid then?
It's not exactly the acid because the acid is the HA together. Technically, A minus is always the conjugate base of the acid. It's the thing it turns into when it gives up its H.
So how do you know, how do you remember to put it as that? So
Because
HA
you'd be
is
like
HCl?
giving it to you in the problem, yeah. So like we'll look at a problem in a second and I'll show you like what it is
Oh,
in that
like in the
problem.
word problem it'll say HCl and then
Yeah, it'd say like
HCl.
what it is. But like as we model it like in our beaker, I'm just using HA so it can apply to any problem we deal with. Yeah, Jack?
So A is always the conjugate base.
Yes, A minus is always the conjugate base though.
Is it always negative?
Yes, because it's always what comes when you give up the H, which makes it negative. So good observation. All right, as I mentioned once again, the little a is simply just to indicate that it is for an acid, but it's no different than every other K we've learned. Those two equations you just wrote, by the way, are on your formula sheet of that HA, A minus. Once again, it's just products or reactants, but it's always there. And then it still represents the same thing. So what does a K value tell us about an equilibrium? Alex?
Like the acids, like dissolved acids compared to the non-dissolved.
Good, right? It's that ratio of products to reactants. So it's the same thing here with acids of the K value helps you know how much products compared to how much reactants. Now we have an interesting relationship here as we've used the word weak and strong, right? By definition, if I call an acid weak, what does that mean about my beaker?
There's high pH, right? Or, yeah.
Not exactly. Could be, but if it's strong, what is guaranteed about the beaker? How would you change your beaker to make it strong? What would you do?
All of them are put together.
All of them are apart, right? So by definition, classification-wise, strong, all broken apart, weak are mostly together. Now, within the category of weak, you can have strong, weak acids. What would that be claiming if something was a strong but still weak acid?
Wait, so weak is more put together? Oh.
I know, it feels backwards because most people think strong and they think of holding together, but strong is about letting go. No.
You shake it and it makes it strong. If you have a weak acid, you just have to shake it into a strong.
Good. So what Lindsay said, have a smiley face for that, is if something is considered a strong, weak acid, it means they're not all broken apart. But
They're pretty close.
more of them are than in another one. Yeah, Lily.
So when we're talking about like strong weak acids, is that like a defined group of
Hold up, I have a second.
weak acids, or is that all comparatively to whatever?
Great question. It's really more of a comparison idea. So for example, everybody look at this list up there. Oh no, I didn't erase it. Oh, I just highlighted it.
Oh, I wonder what it is.
Okay, so which one of these would be the strongest of the weak acids?
I don't know.
No clue.
We'll cut that out of the video so they won't.
Oh, now you have to actually edit it.
So, why is this one the strongest of the weak?
Because it's the highest number.
Good. Oh my God, it has the biggest Ka, right? So the bigger the Ka, that means the more it's breaking apart, which means the more H is floating around in the water. So yeah, so like Lily said, it's really a comparison when we're using the strong of the weak, classifying it as just weak or just strong, that is a distinct groups, I guess, categories.
Very weak acid. All Ks.
Okay, the other way we can measure how strong or weak something is by its percent ionization. Now, in general, what is a...
Is Caleb Coulter to check out?
Yep.
right, Caleb.
Can someone define for us in general, what does a percent measure? Any kind of percentage?
The amount of it
Yeah, so we typically have a smaller number over a bigger number. If it was for calculating for a test, what's the bottom number?
how much there is.
Yeah, the total amount, right? All percentages are that way. Where the bottom represents the total amount. So in our case, it's the amount of the acid itself, the original concentration. And then the top, like on a test, that's how many you got right. In our case, it's how much was made. So it's how much H plus there is. So for example, with the beakers on your table right now, you started with 10 acids together, right? And then the percent ionization would be how many broke apart compared to the original 10. Okay, so it's another way that can identify the strength of a weak acid. All right, let's try a problem here. All right, so same problem we did as before. It's the same exact question. It's saying, what is the pH? Okay, so my thought is, whenever I'm problem solving, is I say, okay, well, I need to find pH. What is pH? How do I calculate pH?
The amount of flooding.
Good. pH is a measure of the negative log of the floating H pluses. All right, so that's what I need to find. Now, when we did this last time, we knew that the 0.3 that was given was the amount of the H pluses. Why is it not this time? It's not a strong acid. So it's the next thing you need to make sure identify is this is a weak acid. And I know that from two things. One, there's an equilibrium arrow. Two, they give me a Ka. And strong acids don't have either of those.
Okay.
Now, we are going to go through a similar process as we did before, and we're going to set up a rice chart. Okay? So we'll set up our rice chart here.
No, these things
Hey, stop complaining.
are not my favorite. I don't remember them
Be
ever.
grateful you can learn.
Yeah, maybe.
What do I know that I can plug into my rice chart from the problem? Okay, where did that 0.3 go?
Below the HCG.
Yeah, that's our original amount of
What?
our acid.
HC2,
Okay,
H2.
now I'm just going to cross off water from our rice chart here because it
Don't do it.
is a pure liquid, so it doesn't matter. Okay, now once again, to connect it to your models on your desk, this would be HA, this would be H plus, and this is your A minus. Okay. All right, what else do I know that I can plug in?
Zero.
Good, I know these are going to be 0 because it hasn't broken down in the beginning. It's the conjugate from the beginning. Yeah.
Alright, yeah.
Okay, now when it was strong, what did we say?
All of it is a.
Yeah, we did minus 0.3 because all of it broke apart. It's not all breaking apart because it's weak, and we don't know how much it's breaking apart, so we're going to say,
Times 1.8.
Minus X
okay, and then these would be
plus X.
plus x and plus x.
So it's X.
Okay, so we're going to carry that down, so this is 0.3 minus x, x, and x. Now what is it I'm trying to find here? X, because x is, right, my H plus up here.
So is Ka X?
No, but we can set it equal to solve for x. So, what is K equal in general? What's the setup for any K? Products over reactants. So my products are these two. So Ka will equal x squared over 0.3 minus x.
Well, X times X is X.
Wait, why are those times,
Because they're both on the top of the fraction, so x
Oh,
times
right.
x. Yeah, good clarification though. All right, questions so far? How I went from my rice chart to my K equation. So once again, we just plugged in our products. Okay, so these are our two products over our reactant.
Why do you
Okay, now we just need to solve for x. Now, as it's written, you can solve for x with this equation. You're going to end up having to use the quadratic formula or graphing and solving for x. Because when you have an x squared and an x, that's the only way to do it.
No, it's not.
Or you
But-
could, can't you just square root?
So you
Oh
have
wait,
x
never mind.
by itself.
Yeah.
There's a shortcut that we can use, and it will work every time in this class. Here's our shortcut. Now, with this a shortcut, it's based off the fact that we know this is a weak substance, right? We know it's a weak acid, which tells me what?
It's not all.
It's not all broken down, and to be honest, it barely breaks down. So we're gonna make an assumption, and I want you to write this assumption down, because it's important to recognize why we're allowed to do this. Okay? We are assuming that 0.3 minus x, which is the change of the from the original concentration, is approximately, and those are squiggled equal signs, which means approximate. You didn't know? 0.3. Now, it's important to recognize, is this assumption saying x equals 0?
It's saying it's very close to zero.
Is that the change is so small, right? So we're not saying x is 0 because that would just make the whole fraction 0, or right, 0 over 0.3, right? We're saying that the change from 0.3 is so small that it really doesn't change it much at all. And if you ever want to try, if you solve it through the quadratic and with the shortcut and round according to sig figs, you'll get the same answer. So it works every time. Okay, so what that means is it's going to change our setup here from this setup to now it's going to be x squared. So in blue is what I have after our assumption. 0.3 equals 1.8 times 10 to the negative fifth.
Is that a less than sign?
Yeah, is that anything or is that?
Yeah, this is like how you want to say these two things are equal, but not like a direct equal. It's like I'm changing this equation to that equation.
Is that a secret smiley face?
Wait.
I mean,
I
it
had
looks
a
like it.
So is it-
I had a very particular math teacher in high school, and so like if we did not have like the correct equal sign or symbols, like we use points.
So it is a smiley face.
No, it's not a smiley face. It's a real thing. I don't know if it has a name, but that's what you do when you have. It's saying that this whole thing
Okay,
is equivalent to this,
okay.
or like we
Very
transition
close.
it over.
So we can find out what it is.
Did you learn that? Yeah, not this. Do you know what it has? I don't know if it has a name. Just like arrow. It does look like a secret smiley, though. I would you down.
You know, I'm
So every
thinking
time you write it, do we get a smiley?
If you see it, I guess. Okay,
Oh.
good so far?
we have to like look back at you to try and find the secret smiles, and I think that takes away from the learning experience.
Oh, I don't ever do secret smileys in moments like this. They're happening when everyone's talking and no one's looking at me. Okay, now we need to solve for x. So, algebra, how do I get x by itself here? Because I'm going to times both sides by 0.3. Ends up being x squared equals, I don't remember when I put this in there earlier. 5.4, I think.
Way to hear the word.
4.5 times 10 to the negative 6. No, I said that backwards. I meant
5.4
5.4 times 10 to the negative 6.
You got square root is
Okay, now we can just square root both sides.
equal
I was
to
just
0
thinking.
And so then x equals 0.0023.
Oh, okay.
Okay. Now, before you get excited and just circle because you found x, is x our answer?
No.
Good. What do we need to do with it?
Plug it in.
Plug it in.
Yep, we got to take the negative log of that thing. Right, so we're going to take, so pH equals negative log of 0.0023, and we end up with a pH of 2.63.
Wait, why is that the
Two
original?
point six four.
Say that one more time again.
Why is that the H plus?
So X, right, is the amount of H plus that was created. You see right here from like our rice chart, right? It's how much gets made as this breaks down by that same value.
Okay.
Any other questions before I have you try one? Yeah, Emily.
So the x is 0 for like 0.2 minus x and not for the x on top?
Yeah, so that, because once again, it's the idea of here is it's more if we're saying the change is negligible. Like it just barely is changing, and so in comparison.
Jeez.
Which technically, once again, if you minus, like if you take 0.30 and then you minus what our x value was from it, it's like barely changing, and with sig figs, it like almost goes away. I think of it as like if I were to step on a scale and take my mass, get off the scale and pull a hair off my head, and get back on, did my mass go down?
No.
Yes.
Yes, but is the scale gonna show it?
No.
Not unless I have an extremely detailed scale at my house, right? Like, and so it's kind of that idea of where it's just so small, it doesn't make a difference. Any other questions on that? Now let's use that value, and now we're gonna calculate the percent ionization. So percent ionization is how much H plus was made. So what was that value we just found?
0.002.
2.6.
Is it 6? 2.6?
3.
2.6. Oh, that's the pH.
Not the pH,
Oh.
the X value, 2.3. So this is how much H plus was made. If you want to draw an arrow up to the problem above so you know where it came from. Over the original amount, so 0.3. And then of course times by 100 to make it a percentage. Which ends up giving us a 0.76% ionization. So if I had 100 acid molecules in your beaker, less than one of them are breaking down, right? Which once again kind of justifies the fact of assuming the X
What is
away.
1.8
So,
times 10?
okay, questions before I have you try a problem with your table? Okay, I'd like you to try practice 8.3, do A and B. I'll give you about 6 minutes. If once you have it, check with your table. If you all agree, raise your hand and I'll come check y'all for 2 smiley faces.
If you have an extra calculator, mine does.
Yeah, you brought this one. Okay.
Thank you.
Yep. All right, ready, go. 6 minutes, 2 problems. Let me know if you need any help.
It wasn't that last time. That's all.
This one is similar to what you'll do on tonight's homework.
Oh. Why did you just do that?
Wait, isn't that what you all picked? Is that why you picked it? Once again, I know you're not with your normal people, but you can still talk to each other while you solve it if you want to. Or you can wait till after.
What is going on?
And that's kind of the catch, is once you see like how it works, you can use that.
Question.
Yeah, because acids on bases are always
X squared.
1-to-1 to
What if I'm drawing my own
ratio.
secret smiley
So
face?
always
Do I
ends up
choose
being
from that?
X squared over fraction.
10 to the negative fourth, and then you do some algebra stuff.
Okay.
If it's easier, Ellie, too, is the T left, if you want to move here, that makes it easier to see. I know sometimes these like aren't the best position, but it's up to you.
5 to the times 10.
Once again, once you have it, compare with your table. Once you all agree that you think you've got it, raise your hand and I'll come hopefully give you some smiley faces.
What's the big one that you guys did? 6, 7. pH.
Did you guys get 2.17?
Slow down. Dude. What'd you get?
2.17.
Oh wait, I did the wrong one. Negative log. What did you get?
2.17.
So what does X equal?
Accidentally did.
Does it, well, it doesn't equal K by itself. So like what were you in your rice chart? Or what were you trying to find overall? You're in? So what do I need to find
Do you not
pH?
have a graphing
What's the
calculator?
equation for pH?
How are you surviving
I
that?
forgot, I'm not gonna lie.
The negative log of the.
Yeah, negative log.
Yeah, so that's what you do.
He's like graphing stuff in his mind on the graph.
That's what I do for the unit circle.
He's like just graphing parabolas in his brain.
You guys get 2.68 for the
2.68?
X equals negative.
Oh, for the ionization amount? I'm like, dude, what?
What you got into?
I mean, probably.
If I got the one thing.
I haven't checked it.
Testify later, Zach.
Yeah, but you
It says
could be
water,
wrong.
and I'm just putting water in it. You let, in case people question, that I
And then
actually
2.68%.
No, it's not,
use water.
Oh, yeah, it's not the
Yeah,
stupid.
it is water in the water beaker,
It's water in the water beaker and nothing else
and
besides
nothing else. Okay.
Yeah,
And Marissa,
and then the
it says
ionization.
sodium hydroxide, right? Yes, and I'm putting
my bad,
in the
guys.
one that says NaOH.
I failed
Yes.
all.
I'm not tricking anybody here.
2.68.
Did you get, 2.17 and then 0.027?
Oh, that wasn't the one I wanted to use though.
I know.
Wait, that's actually really strong.
I
That's
got
actually really strong.
No, it's not.
Wait, no, ionization.
Oh, 'cause you got it by
It's
100.
breaking off that's ionized.
So.
To make it
It's super weak.
Yeah, 2.
So it's gotta start lifting.
It still says.
This one, like you stick it on your
Grab the
finger
wrong
and like,
flavor.
this one's like pineapple.
I
It
think
just makes your
pineapple.
tongue
No, I
go.
think pineapple's more acidic than this. It's not visa.
Yeah.
How acidic is pineapple?
It's pretty acidic. I don't know off the top of my head.
Is it like battery acid acidic?
How acidic is Red Bull?
Wait, she's thinking.
Red Bull.
It is
It's-
battery acid.
What?
I don't know.
I mean, I wouldn't be surprised.
That's why I keep
People say
doing
things
You die. You turn into an angel.
Okay. Some people look red. What did you guys say?
Lie.
I am so.
Oh wait,
Two point one seven?
Hey.
2.7%?
What did you get? 2.17 and 2.6.
Who?
Okay, are we ready over here?
It just takes me a while to do that. Oh, no, you're good.
Good, and percent? Good job, have two smiley faces. What do we get back here?
Okay, on a pH scale, do you just round to the nearest whole number?
Are you guys ready over here?
Yeah.
What do we get for our pH? Good, and percent ionization?
Do you want to, do you always want to round, like, do you want to round to the whole number on the pH? Or do you want to?
No, you would never round to the whole number.
Hey,
The rule, logs can have a weird,
Have you looked at the workout?
Just to let you know.
but.
Hey, what are you doing, Dad? Oh my goodness. You just stole his hat.
There's 3
What?
groups. That's
Oh,
it.
wait,
Okay, what do we get for our pH?
I have no idea.
It's basically
Where did it
all
go?
the boys.
I don't know.
And then we're in a group.
What is it?
That's your X.
I don't know what that is.
But your X is right now.
And
And then.
then all of the girls
Yep, good, have
in
two
the group
smiley
ahead of us.
Watch this, watch
Jake
this.
and Ashley. And then the third group's us.
So we can write an equation.
And the rest goes off with all the person.
Yeah, so if it doesn't give you one, then just write the equation of the acid going breaking down.
The first person. So we're gonna have like the rest.
Didn't even notice.
Or you can have water.
There's 8 in one group.
I'll get lights too, that means.
Good, any questions?
Ugh.
Okay, have two smileys. Good job.
My head is.
Okay, did I check you guys?
No.
I got it.
Yeah, 2.18.
Good? Good, have two smileys.
You gotta come off the street. I just found it though.
Okay, I think I checked everybody. Is there anyone I didn't check? Okay, eyes up here, everybody. Let's move on to our next topic. So your main homework tonight will be practicing that calculating of pH. 2 words of caution. Number 1, on the homework, some of them are strong acids and some of them are weak acids. And obviously the process is different, so make sure you pay attention to which one you're dealing with. Okay? The other thing is there are some on the homework that are bases. So if it was a weak base, how do you think the process we just did would change?
If it's a weak base.
Yeah, what do you think, Lily? Not quite, but you're on the right track. We are going to use a different equation to flip it.
Well, it's just whatever.
still would subtract it because it's still like breaking apart as a base, or it's still like changing. So, Alex, do you have a thought?
Would it just be, instead of finding the negative log of 8 plus, would be of the base instead, and then use 14 minus that number times the base?
There you go. So doing the same process would give you pOH. So to get it to the pH scale, you just do 14 minus. So just a few notes when you're doing the homework, that you don't get so lost in the process and you forget like, oh wait, this is a base, I need to do it a little bit differently. Or once again, if it's strong versus weak. Okay? Our next thing we're going to introduce today, and then next time is going to be all about it again, are these things called a buffer. Okay? Now a buffer is a substance that is created or used to regulate a pH.
Spread it quick.
Don't worry about that.
It is not going away. It is stubborn.
It was doing it.
So, before we get into buffers, let's remind ourselves about acid and base reactions. So whenever you have an acid and a base and you pour them together, they will react. Now, we talked about there's certain patterns if it's strong and strong. What do we see if it's a strong acid reacting with a strong base?
The H2O.
It always makes water and a salt. So label that for me here. Which one's our salt? Good. Now in our case, once again,
It's not writing. Wait, you're telling me.
right, so this is your salt. Keep in mind, salt is anything ionic, right? And don't get confused that it's only NaCl, okay? Now, we always have this pattern when it's strong and strong when it comes to the net. In this case, we're mixing sodium hydroxide and hydrochloric acid. I'm going to show it to you in a second here in real life. But the net ionic equation always has the same pattern. So what's the difference between an overall and a net ionic equation? What are we getting rid of, right?
Spectator ions.
Good, yeah, those spectator ions, the ones that are just floating around before, still floating around after. So the way to get to a net ionic equation, this is review here, but you have to look at each piece in its true form. So sodium hydroxide here is a strong base. So it doesn't exist as NaOH together, it exists as Na plus and OH minus because it's a strong base. HCl is a strong acid, and so it doesn't exist as HCl together, it exists as H plus and Cl minus. All salts exist as separate things, right? Positive and negative things. So this would be Na plus, Cl minus. And then the water, though, should stay as water, because that's how it exists. Now, who is spectating our party here? Good, so Cl's floating around here, floating around there. Who else is spectating? Good, so Na, Na, and so those get removed when we write the net ionic equation. And so the net ionic equation shows us making water. And that will be the same for all strong, strong nets.
You are right.
If it's a strong and strong, it's always going to have the same exact net ionic equation.
Huh.
Now, as we mentioned before, does that mean
Super awesome.
it's neutral? Right, so I have some hydrochloric acid here. I'm going to add indicators to prove it to you. Right, so here's our acid. So this is the universal indicator. So remember, this is the one that does the whole spectrum of the rainbow for the pHs.
Whoa.
Just add in. The more you add doesn't like change the pH, it just makes it more vibrant of a color.
Oh yeah.
And I lost my stir stick.
Okay.
It's fine. Okay.
Second slow.
So if I pour them together, what am I going to make?
Water.
Salt water, right?
Can I drink it? So it's drinkable?
Oh, I guess I'll pour them in this way.
Well, I don't know what I'm expecting. Whoa, it's increasing in volume.
Oh.
I'm sorry.
Okay. Now,
It's dying.
why is it not neutral
Because
if I made salt water? Why didn't it go green?
It's soluble.
Did I make salt water?
Yeah.
I did. But why is it not at neutral?
I got a degree.
That was last time.
I say we nominate. I'll just do it.
What would cause it to still be, in this case, it's more basic than it is acidic? Kinsey, your thought?
Is it because H2O can be both acidic and a basic?
Not quite, but good try. Have a smiley face for that. Anyone have an idea?
They didn't.
Is there just excess base
Yeah.
in there?
It's just, in order for it to go perfectly neutral, you have to have the exact same amount of acid as you do the base down to the individual atom. Right? If you have one more base there, it'll flip it to basic, right? Or one more acid. So in this case, obviously, I tried to measure 100 mils of both, but obviously it
Wait,
didn't.
so how much more basic?
Have
would
you ever got it
make
perfect?
Like, can you still technically drink it?
Well, I wouldn't now because it does have indicator in it, and that's poisonous.
Oh.
With indicator, I would not. Yeah, Jack.
Is it ever realistic for them to be equal, like ever?
Great question. Only when it's done through very controlled settings, which we'll learn about not next time, but the next time, where you're literally adding it drop by drop. And
Have you
then
ever
you
come
can get it
close?
to be closer. But even then, right, like how many atoms are in the drop, right? So, yeah, Porter.
So if you like added some more in there, you couldn't get it to.
I tried just by pouring, it comes out too fast. So like last period I tried to add some more acid because same thing happened.
Use a dropper.
And then it went the other way, but I never got it to go green. So,
Use a dropper.
but yeah, if I did it slowly with a dropper, which we will do in 2 days from now.
Is that titrations?
Yes, and it's called a titration, yeah. Okay, let's look at the difference now of when it's a weak with a straw.
Finally. I'm the best
I'm really,
at getting things wrong most of the time.
wow, why does it do that?
It's because you drew over it with a different marker, and it's erasing.
Oh,
the
is it
top.
erasing like one at a time
Yeah.
color? Okay, so key thing to notice here, right? Recognize we're looking at weak versus a strong now. And here's how it changes. So, since HA, we are saying is a weak acid, we keep it together.
It's not very nice.
So with a net ionic equation, you don't separate weak acids because most of them stay as HA. Now, NaOH is strong, so that one we can show broken apart. Now, mine has a typo. Yours is fixed. It's not NaCl because Cl was never there. It's technically Na, little big A, right? So this is what is on your paper. This is still a salt because Na is a metal,
Yeah.
right? So this would be Na plus and A minus, and then water. So keep in mind, just because you make water, right, doesn't mean they're both strong, but it's then what comes next. So who's spectating this? Just Na, right? So we only have one spectator this time. It's just the sodium ion. And so we'd have Ha plus OH minus to A minus and H2O. So once again, recognize the difference between strong net ionic and then weak strong. Okay, let's look at a buffer now. So what I'd like you to do is I'd like you to make your beaker that's on your table look just like this beaker. So you should have 1, 2, 3, 4, 5, 6, 7, 8 HAs, 1 A minus and 1 H plus apart, and then you'll have a spare that you're not using. So pull out one completely and then make it match mine. And then we'll show you a buffer demo here.
And you said you want us to take one out?
Yeah, so you should have a spare one that we're gonna throw back in later. So 8 together, 1 apart, and 1 spare. Everyone have that match? Okay, let's look at, first off, something that is not a buffer. Okay, so a buffer is a solution, and we'll talk once again all about it today and next time. But the objective of a buffer is to regulate pH. Meaning, if some acid is added, the pH doesn't drop. Or if some base is added, the pH doesn't shoot up. A real life example of a buffer is your blood. Your blood has a very specific range it needs to stay in to keep us alive. It's like, oh, I should have looked it up again. 7.35 to 7.4-ish. It's like very small range. And if you go below that, then you go into blood acidosis.
Yeah.
And if you go above it, then you go into, I can't remember what it's called, when you're too
Something bad.
something else. That's not good, right? And like literally death could occur. Okay? But that means we don't want, just because I eat something that's slightly acidic, I don't want it to drastically change my blood. Or like when you exercise, you produce lactic acid. You make acid and that happens, but we don't want that to drastically alter our pH. So a buffer is able to do that. This is water. Water is not a buffer. So I'll show you what happens to something that is not a buffer. So we'll add some indicator here so we can actually see it happen.
Is that pure water?
It did come from the tap. So, you know, I do drink it, if that helps. I drink my tap water. Okay, so there's our water. I'm gonna add some drops of sodium hydroxide. So right now it's at like a neutral pH, and I'm gonna add some base to it. Okay, and then we'll watch and see, oh, I need that back here, the effect that it has. Okay, the goal here is to add 4 drops is what I'm shooting for. 1, 2, 3, 4. Sometimes drops are hard to control. Okay, so 4 drops. And what did the pH do? Shot way up, right? From 7 to like, I don't know, probably almost at 12 maybe or so, right? Because they're like blue purple.
That's like.
Okay, we don't want our blood to do that, right? Where the smallest drop of something makes it change. So now let me show you a buffer and what it's able to do, okay? We'll talk, I'm gonna make it in front of you. I'm not gonna tell you what I'm doing because we'll spend a day talking about that here in a moment. But a buffer is something that's created. It's not just like its own thing. And then I'll add some indicator. Now with a buffer, buffers are designed to regulate a set pH in that specific pH. So it doesn't mean they're neutral. Okay? For example, our buffer that I'm going to show you is, I can't find anything I need. It's an acidic buffer. So it wants to stay in the acidic range that it's at. You can have basic buffers, you can have neutral buffers, just depends on what you're trying to buffer, right? What are you trying to maintain? Okay, so there's our buffer. It's been created. I'm going to add our indicator so we can actually see if it's working. Okay, that should be vibrant enough. That's working really great today. Okay, so same thing. I'm going to add 4 drops of the base to our buffer. Right? Good response.
What if you
Doesn't
add
change
more?
at all. Okay? So let's add a whole squirt of it. Okay? Now if you watch really closely, you can like kind of see it buffering in action. So watch like right where I squirted in. But then right? So like you can see like the pH change as it directly hit. Now, do you notice a slight color change from the beginning though?
Yeah, it's a little orange.
So buffers have capacities, right? It's not like I can infinitely just pour this in and it will just forever work. Or, so eventually you can get to the point where in a sense you break the buffer. It's not broken yet because it's still within like an acidic range. But anyway, so turn to your table buddy and tell them what is the point of a buffer. Ready, go. What's its objective?
Keep it in a specific range. So that it doesn't so that you don't die.
Are all buffers acidic?
No, I just made an acidic one. That has a basic one too.
But I think there's
Yeah, you can make neutral ones. Because our blood is like fairly neutral buffer. So yeah, you can make a buffer at any pH you want to maintain that. So, okay, so you should have hopefully said, right, that a buffer is, the objective of a buffer is to maintain pH. Now, phrase of the unit, what is pH measure?
The amount of hydrogen floating around.
Amount of hydrogen floating around.
Alone.
Right, so somehow the buffer is able to control, even if more of that is added, that it doesn't change.
So does it make it, like, does it make bonds with the H?
Yes, so I call it, there's a battle that goes on, which in a sense means they're reacting. That there's something in there that can react with what's added so the pH doesn't change. Now the cool part is I only showed you adding a base just because of color. Buffers work in both directions. If I added more acid to that buffer, it shouldn't drop even more than where it's at. So it's this thing where they need two species that can battle either direction. The two things we need to battle are either H+, because that comes from an acid, and O-, OH-, because that would be like a base being added. But then the catch is, we can't have them cancel each other out. Because if those two things cancel each other out, then they're not there to battle something new. Okay? All right, does everyone have this filled in? I scroll away from it. Okay, come back up to this picture here. So this right here, clarify, this is a weak acid. Label this beaker. This is the weak acid.
Weak.
Okay, losing my pencil.
It's in the book.
Okay, so this right here is, oh, this is our weak acid. This is the buffer. All right, we're gonna play. One of these things is not like the others. How is the buffer different than the weak acid? Talk at your table, ready, go. And highlight the difference.
Yeah, I really love that. That visualization there.
The amount of the H positive ions
They can go either way, it can soak up the.
they take out 3 less H.
Only atoms. There's less H. What do you
The A's don't, like, they don't change.
Okay, eyes back up front here.
3
Pull out 2 highlighters for me. You want to point this out.
They would rebel.
If you were to put battery acid in a buffer and they drink it, would you like live?
So keep in mind, just because it's buffering, it doesn't mean it's safe, right? Like, because this buffer's like at a pH of 2 still, and you probably don't want to drink it.
Well, like if it's like a somewhat basic buffer, so that it like somewhat cancels out.
So if it was like a neutral buffer, right, and you added that to it, then it theoretically would be safe to drink.
Theoretically.
I wouldn't try
Science
it.
experiment.
Theory only takes you so
I
far.
mean, you'd also have to consider what the buffer's made out of, right? Like, is the buffering solution a safe solution in general to drink?
Wait, are you saying battery acid would be safe?
No, I'm saying the battery acid would get canceled
It's the
out.
buffer.
But the thing that cancels it out is that it's safe to drink, right? Because the other thing is, just because something's neutral doesn't also make it safe to drink.
Are they usually not safe to drink buffers?
Yeah, I wouldn't recommend it.
What was that one that
So
you used?
pH what like determines if something's like poisonous or not?
Not entirely. It's just pH is the measure of the acidity of something, or the alkalinity, which is the basic side, right? Which is just how corrosive it would be to your body. Because that's what acids would do to us if you drink them, is they would just corrode your esophagus and your tongue and everything else. But it's not actually, I wouldn't consider it a poison. I consider it corrosive. So yeah, good question, Gavin. Ian.
So if you just drank something that was really, like it had more alkaline, like if it was too much, is that a thing? Too
Yeah,
much?
that'd be like drinking bleach.
Oh, okay.
Oh.
Don't do that.
So that's also.
It just reacts differently. So instead of like corroding, but that's almost a little bit more on the poison side of how it interacts with your body, than like acids where it would just like corrode everything. But yeah, still not good to do. Okay, so with the difference here, here's the two things I want you to highlight. Okay, this right here is just a weak acid. And it technically has the pieces to the buffer, but what's the difference in the actual buffer?
Or A minus.
More A minus. So in a buffer, we need a fairly, there's our squiggly equal sign again, okay? Once again, I didn't make that one up either, it's a real theme, okay? We need a fairly equal amount of those two things. A weak acid by itself doesn't have that, because once again, it's like 99 to 1. So we need to do something, so buffers are made often with starting with a weak acid, that was the first thing I poured in, but then we have to add something else that can help increase that amount of A minus. Okay, these are what I consider the two battling species you need in a buffer. Okay, all right, turn to the next page and let's talk about how they battle.
Really, if you can use,
I wouldn't want
what's the
to
most usually used? They do like colonial times, like line up.
That's kind of nice that he erases it piece by piece, but it's kind of weird too. Okay, so change your beaker, because right now it's a weak acid. We want to change it so it's now a buffer, so make it look like this. Okay, so you're either going to take out, you should only have 5 HAs together. You should have 4 A minuses alone, and then 1 H plus by itself. And then you're going to have just some spares pulled off the side.
Unusable, man.
Okay, does everyone have their beaker set up like a buffer? All right, so our first objective here is why does the pH not drop when a strong acid is added to the buffer? So put right here, mine still states, so we're going to add some more acid. We're adding strong acid to this buffer, which in a sense is adding H pluses. Technically, there's going to be some other random spectator coming along with the H, like Cl or whatever, but we're just going to focus on the adding of the H plus. Okay? So, grab 2 H pluses that are not in your beaker. This is you pouring acid in. Now, if pH is not going to change, what has to happen to those extra H's?
They need to attach.
Something has to bond with it, so who's it going to bond with? There you go, good. So the battling species, when we add the H, so I'm going to highlight them here, right? So as those H pluses come in, so those ones are going to be in pink, they are going to bond with the A minuses. Okay, so let's draw an after picture here of what's changed. Okay, so this HA, so once again I'm going to keep them lined up the same. This HA hasn't changed, that guy stays the same. But this A minus is now bonded with the H that got added. So notice I'm adding, so that one right there is the H that was added, bonded with that A minus. And so then we have this HA stayed the same, this one stayed the same. We got another one here that bonded to the A minus. Once again, so my highlighted colors are to match up to my before and after just to see where it went. So those H's that came in, and we're just saying for example's sake, we added 2 of them. And so then I still have some H plus by itself. But since the H plus by itself, since that amount, right, there's no more of it, there's one here, still one there, is the pH changing? No, because this H plus is what measures pH. And so if there's not more of it floating by itself, then the pH should go up, or down, I guess I should say in this case. Would you consider this, is this an acidic or a basic buffer? It's acidic, because there is some H floating around, right? So it's going to have a low pH.
Wait, why doesn't that H bond with any A minus? Cause it has to keep.
Great question. It comes from the fact of, is everyone good here? And we'll scroll down to the equation. This should hopefully link it up with what Levi just asked. So we'll look at the equation and that should answer your question, Levi, but good observation. Okay, everyone okay here? Okay, so looking at our equation then, well, let's fill in this blank and then we'll answer this question. So these were blank on purpose. So based off what we just did, the what from the strong acid reacts with the what in the solution? Good, Gavin has a smiley face for that. So the H plus from the strong acid reacts with the? Good, A minus, which, once again, by name, is the conjugate base. All right, we're going to make some little bar graphs to represent the amounts, to kind of just, once again, reflect it in a different way. Same thing our picture just showed, but just a different way of looking at it, okay? So in the beginning, before the acid was added, right, I had, for example's sake, we're going to say I had this much HA, and I had almost the same amount of A minus, because it was a 5-to-4 ratio in your before beaker. Once again, so that's the idea of a buffer should have fairly equal amounts of both. Okay? Then, what happened though once the the H plus was added? What got used and what got made?
The A or HA ratio.
Good, so A minus got used because it reacted with it, so this should go down. But then HA goes up. Because this is, the A minus is what reacted with the H plus. And then the HA got made in the process. So the reason why, Levi, there's always some H plus floating around is the idea that HA is a weak acid. And all weak acids that are at an equilibrium, and so there's always going to be some amount of product. Even if it's taken away, the equilibrium will shift to make a little bit more. Because there's weak acid in our system. Yeah, Jack.
If you're constantly adding acid and base, will you just never run out of the buffer?
Great question. Yeah, because in a sense, then the graphs would fix themselves, right? That was my face for Jack. Good observation. Okay, questions on what a buffer is for now? Okay, we're gonna stop there because I don't want to rush the next little bit.
I say we do it.
Next time we'll continue on, but look at it on the opposite side of if I add a base to a buffer, how does that balance it back out? And then we'll talk more about how they're made and then some calculations with them as well. So tonight's homework is just about the pH calculation stuff. There's nothing about buffers yet on the homework. It's just calculating pHs.
What would happen if you combined acidic buffer with basic buffer?